This work will be very much aligned to the last talk you saw, but the very end of the last talk, when he was doing the simulations for Hosler and so on. So I'll try to address the same problem. So just to recap, so I have a network dynamical system. So by a network dynamical system, basically I mean a triple. So I need two things to define a network dynamical system, which will be the graph, which is telling who is interacting to who is neighbor to whom. Then on the top of each node, I'll have a dynamical law that says like, if this node were to be isolated, how would it evolve? So this is a modeling by F. And then I have to predescribe the way two nodes interact, or how they talk, let's say how two nodes feel each other. So if you give me this triple, I will say that I have a network dynamical system. So isolated law, when they have to evolve, how do they talk to each other, and the graph structure. Oh, I see here my part of my slide quite don't fit. I think it's okay. I just had an equation, which not so important these days. But I can write the equation. So basically, the equation is the following: it's saying that I will say xi is the state of the node I, and let me say xi bar. So there will be the next state, so t plus 1, so I don't have to write time. Following Russian tradition, right? Yep. Yeah. So this will be f of xi. So this means like if this node was isolated, the evolution law would be something like this. Now I have the network effect. This will be alpha sum aij. So this is the adjacency matrix that we heard last talk. And here will be h of xi, xj. So this will be the equations I'm be considering. This is basically the equations you saw in the last talk. Alpha here is the coupling strength. I'm assuming that's going to be small. So if alpha is 0, you go back to isolated. This aij is the graph G that says who is neighbor to whom, and h is the coupling function. And this is a network because this h depends on only 2, right? So it's pairwise interaction. So I'll have 3 assumptions here. So I will assume that f is chaotic, whatever that means. I'll make it precise in 5 minutes. But let's say the behavior of f is very complicated. I'll say that alpha is very small. This is my 2 main things. Yeah. So from this behavior of f very crazy, chaotic, alpha very small, I want to now I want to. So this is not okay, right? Let me try to. Maybe this works. Okay, let's check the same equation. Just here, maybe showing off a bit, right? So I'll denote the x without any index. That will be the vector state for the whole system. Yeah? Okay. Yeah, so I will assume the following. So let me do this now. I will assume, assumption 0 we'll call, because this is basically how the whole thing starts. We measure xi times t from 1 to n for all nodes from 1 to capital N. So capital N will be the number of nodes I have, and the small n is the length of the measurement I did. So I'm assuming that I measure this for all nodes. Yeah? And the goal is from these observations is to reconstruct the graph G. Along the way, I will reconstruct F and H as well, but my goal is to reconstruct G. Okay. So then I will start with assumption 0. So assumption 0 is that my network is sparse. By network being sparse, basically I mean the following, that each node locally has only a few neighbors. Yeah? So they could have n neighbors, but it has only a few. By only a few, we'll make it precise also in the very beginning. But basically, the number of neighbors of this node is much less than n. Okay. And now, so for any reconstruction problem, I will need, so the whole idea is the following. I will write my dynamics. So basically, I write this equation as a combination of a given basis function. So this basis function I will denote by L naught. So basically, the local dynamics of each node will be a linear combination of these basis functions L naught. So this is the main idea. And for this talk, this L naught will be the basis of homogeneous polynomials. So basically, this means like, if I were to write my isolated dynamics, would be polynomial, and the coupling will be polynomial. I think that's it. So no big deal. But if you're really a good mathematician thinking about some crazy C infinity, I don't know. So this is not entering here. So everything's super nice, very polynomial. So here's the main trick of this whole thing. So I'm saying that the state of each node now is written as a combination of this basis. So I will do this. So if I fix time, I can write this as vector multiplication, right, of the basis. This is matching this equation. And then I do this for all times. So I repeat this process. So this equation here is true for time 0, it's true for time 1, it's true for all times, actually. So then basically I'm saying that I measure from time 0 up to time n. So I do this vector here, which I'm denoting by x prime. So it's the vector of observations. I get this operator here, which is basically the matrix of the basis functions evaluated along the vector of vector states along time. And here's my vector of coefficients. So this equation is always satisfied. Yeah? Is this equation clear? So that will be kind of important. So if it's not clear, so it makes sense to rediscuss. So the problem here is the following. So this equation is true for all times by construction. But basically, usually you have, we measure x, so we know x prime. You can compute these guys, but you don't know c. So you have to invert this problem and try to compute c. So the whole idea now is, okay, I know there is a c that solves this equation, how to get back the c, yeah? This vector of states. So if I compute this vector of coefficients, I know everything. I know f, I know h, and I know aij. Yeah. So the name of this game is to get this vector of coefficients. So let's see what people do. So this problem can be a super simple problem if you really have lots of data. If you really have lots of data, this operator here becomes, let's say, this operator becomes full rank. And then basically you can obtain C just by doing least squares. Yeah? So this means like you measure a lot, so you don't care about the number of measurements, you measure like hell. Eventually, let's say this operator becomes full rank. I mean, why not? It should become full rank, and then you do least squares. You find a unique C, this unique solution, everyone is happy. Now we have two problems. If the network is very large, then the number of basis functions is very large as well. So this means measuring a lot becomes a problem because you can't really measure a lot, so it's too much measurement. Or let's say if the time series is short, so you cannot really measure so much. So in this case, this operator here becomes a short fat matrix. And let's say this vector C is actually huge. And there are two options. So either this system has no solution whatsoever, yeah? Or if it has a solution, it has infinitely many solutions. So kind of how to pick up C. So what people discovered back in the 2000s, that in this situation, if you try to minimize, let's say that you have this problem, you try to obtain the problem by this here, you find a solution. So let's say if you knew the solution was sparse, so only a few entries of this vector C is non-zero. If you try to do least squares, you find a vector C solving this equation, which is actually not sparse at all. So it has non-zero values in every entry. So just to say, in this situation, well, the network's very large. So AKA the time series is short. If you do least squares, it's basically the worst thing you could do. Yeah? So what else to do? So what can you do? So the question here is the following. So by assumption, my network was sparse. Therefore, I should look for sparse solutions. So what people try to do, I mean, this was a typical problem. And as far as I know, that they solved this problem in a workshop in IPAM. So the thing was the following. So let's look for sparse solutions. So some people had the idea, okay, so if you're looking for sparse solutions, what you could try to do is to minimize the solution that you're looking for in one norm subjected to the solutions of this equation. So the idea, okay, let's minimize this guy here for the L1 norm. Whatever I find this, it will be the solution to my system. So the general idea was that if you try to look for one norm, you find sparse solutions. So the idea was something like this. If you plot the true coefficients in one norm, you have this very pointy area, right? And now you try to find hyperplanes of solutions. So it's very typical that this hyperplane will just hit this polygon in a pointy area. So this means that you get a sparse solution. So that was the whole jest. Okay. So they are doing this in this MRI reconstruction. People in networks, they start to do this for network reconstruction. As I said, so you could try to do here L2 norm minimization, so least squares. This will work when the length of the time series is very large. Let's say if the operator becomes full rank, thumbs up. This is very easy to solve. If you try to do L1 reconstruction, this is total mess. Sometimes it works, sometimes it doesn't work. Yeah, so there's not many conditions. So this is back to what Klaus was saying. So how do you guarantee unique solution? Yeah, so let me give you one example where this problem can be traced, and you can see what's going on. So my F, the isolated dynamics, will be logistic maps. So it's a polynomial degree 2. I'm doing the classical logistic map. Alpha is pretty small, so 10 to minus 3. So this H is what we call diffusive, so it will be the difference of two functions. And this function will be a cubic polynomial of degree 3. And then my network will be a ring of 10 nodes. So very small network. Everything is nice. Everything is super nice here as well. So let's try to see what's going on here now. So what you see in this plot, so here's the network, the ring of 10 nodes. On the top of each node, I have this logistic map. So very near to the chaos regime, so B equals 4. And in this plot, what you see in the x-axis is the length of the time series, so how much I measure. So I measure hundreds and 200, 300, 400 data samples. And here what you see is the fraction of what we call false positives. False positives, I'm counting, so whenever I have a connection that was not there, I count as 1, and then I take the fraction of the total possible false connections. Is this clear? Yeah? So you see, if the length of the time series is small, I get trash. Like the false positives, I mean, the network reconstruction is all over the place. And then I start increasing and increasing, still trash, so. And then by about 300, I start to get good results. And then it drops, and then it plateaus, and then eventually will give a good solution. But eventually, when it gives good solution, you're kind of in the full rank situation already. Yeah. So, but let's recap. I'm doing L1 minimization here, so I'm minimize the L1 norm, subjected to solution of the equation. There's a strong sensitivity to the data length. So if you're around here, you get a network that's total rubbish. Yeah? So the main question now is the following. Can you find a condition that will guarantee that if I measure by this much, then I get unique reconstruction? So this is the name of the game. Is the problem clear? Yeah? So even the super, let's say, super simple scenario, everything is under control. If I don't measure enough, I get trash. Yeah? So I can try to, let's say, roughly speaking, the idea is the following. How much data you would need. I do not know how to prove this, but a good heuristics is that if you want these least square to work well, you need to measure at least n square data points. The problem is that the constant that enters this big O is very large. It would depend on the degree of the polynomials and so on. But usually you really need a lot of data. Yeah? So in this case, you see, we need 400 data points. The network was 10, so it's really n squared times 4. So if you're thinking of a large network, so thousands by thousands, you need now millions of data points, which is not possible, right? So if you want the least square to work. So what I want to do now is to do the following. Let's see whether this problem is clear. I want to determine the minimum data length I need to have, such that I guarantee that my solution is unique. Yes? Okay, so this is the name of the game. And if this is clear now, so what are we going to do? I will introduce this idea, what we call, I will do the search for sparse solutions. I do not want to look for any solutions, but only sparse solutions. Okay, so let's do a recap of this important theorem I told you that some people discovered, and that some words will appear, and let's discuss these words. So the idea is the following. The condition they found it was important to get unique solutions for this minimization problem was the following. You take this matrix phi, which is this library matrix, right? The operator associated to the library matrix. You take any set of cardinality 2s. So basically, you take any 2s set of columns of this operator phi. And then this word will appear. They are nearly orthogonal, whatever this means. You can make this precise, I'll do this precise. But basically, it's the following. This operator, so this matrix is a short, fat matrix, right? Okay. We have someone in the audience that likes botany, so probably. What? What I mean is the following, so this condition is saying, so this is the operator phi. It has more columns than rows. So then you take a set of 2s columns. So, and they can be nearly orthogonal. So if this S is too large, then of course this cannot be true, right? Because then this is a contradiction. So I kind of span the whole space, and then they cannot be orthogonal. But let's say if this, anyway, so if I take this 2S, this S is not very small, that is not very large, then there's a possibility that the set of 2S columns, they are near orthogonal system. So this is what they are requiring here. So if you take any, so this is the complication here, so it should be any two sets, that's a set of two columns. If they're near orthogonal, then if you look at the basis per sheet problem, so this problem here, so this is the condition that I'm requiring. So the set of any two columns you can, so the set is near orthogonal when this equation is satisfied. So this is the 2S cardinality, so this is the submatrix of 2S. So by being near orthogonal, I mean by satisfying this equation. If this is true, then there is unique solution to the L1 minimization problem. Yeah, so this is what they proved in the past. So actually they proved in this paper in 2005. Yeah? So the question is now is whether this operator here satisfies this condition. So what I'm saying is the following. So some very clever people, they thought about this problem before us. They were able to distill this problem into a condition that's such that if this operator phi satisfies this condition, then you have uniqueness. What I tell you is now that this condition for us will mean how much data we need to measure, such that this matrix phi will will satisfy the condition they need. But I run into a few problems. First problem, the original operator phi may never satisfy this condition. It may only satisfy this condition when the solution becomes trivial, like L2 solution becomes sensible. Yeah? So I will not bother you with this, but we have examples where this will never satisfy this condition up to the time where the solution is trivial. By solution trivial means like the unique solution of the least square is the solution that you find. Okay, so then the idea that we had was the following. Okay, so this basis L0 is given. So why you don't have to stick to the L0 basis? The idea is like someone gave you a good representation of dynamics in L0. We will go to a new basis, which will be L new. And the idea is that if you look at your operator in the L new basis, then you will satisfy all the properties with the right constants, everything will be right, and the problem will be solved. Yeah? So the goal now is the following. I know an important theorem, which is saying that if some condition is met, my solution is unique. My sparse solution is unique. Then what I do, you give me the problem in a given representation. I will change the representation of the problem and guarantee a uniqueness of solutions. But we have already a few problems around the corner. So the idea is clear, right? So you give me the representation, I change the representation and try to change in such a way that I satisfy some conditions. But to change the representation, it might happen the following. So I told you, so by assumption, solutions in L0 is sparse. Why solutions in L0 is sparse? Because by assumption, the network was sparse. But it is very likely that when I change the basis to a new basis, then this change, there is no sparse solutions here anymore. This is very common, actually. So you start with an initial problem was sparse, you knew by assumption, then you change to a new basis, and in this new basis, you lost sparsity. So this is the first problem you have to tackle. And then if you want, we can discuss that this is actually very typically you lose sparsity. The second problem we have to tackle is the following. So I want this constant that appears, this delta. I want to control delta for many trajectories, right? Because this is a dynamical system. So I choose a point and evolve, choose a point and evolve. It might happen that I control well this trajectory for one point, but for the next I'm screwed. So somehow I need to show that for many, many points I can control this constant. Okay, this is a problem as well. Okay, so let's start now the construction. So this change of basis, what's the idea to change? So the idea now is the following. I had this matrix phi. I take any two columns of this matrix phi. So I will call this column Vi and then this Vj, any two. And then I take the inner product between them. If you take the inner product just by construction, the inner product will be this product here. Basically, it's the following. So here's your initial points. Here's this point at time k, right? Because this is the evolution of the network. And then you sum over k. So this is precisely, if you do the calculation, this is what you get. So this comes for free. So if you're a dynamicist, this looks very familiar to you. This is some kind of Birkhoff average. So I told you the network's dynamics was very crazy, was chaotic. By chaotic, I meant ergodic. And this basically means, by Ergodic theorem, this is going to the average of these observables. So I'm saying there is exercise we need to do. So this is a time average over observables of my basis. There is an important theorem in dynamical systems saying that this time average over observables will converge when n goes to infinity. By the way, I don't want to take n to infinity, but there's this theorem that says it goes to the space average, where this mu here now is the probability measure that's preserved under F. So I'm saying there is a theorem that tells you that this thing here will converge to this thing. Yeah, so this is my ergodicity assumption. So what I'm going to do now, so just for sake of simplicity, I will call this product here psi. So basically, you see, I get this, basically it's just a Birkhoff average. This is what I said. In reality, what I would need to this theorem is what I call, what I need is large deviation, but I will state this large deviation as exponential decay correlations. So I'm talking about two things now. So first of all, let's recap. I realize when I take the products of any two columns, distinct columns of this matrix, the L2, the unit product, will actually be written as time average over this observable. Therefore, by ergodicity, this means like this time average will convert to the space average. This is true when n goes to infinity, which I don't want to do because I told you that a number of data points is important, so I want to keep n small. To be able to keep n small, I tell you the ergodicity is not enough. I need something that is stronger, which is called exponential decay correlation. By exponential decay correlation, basically it means like the system is losing memory exponentially fast. So let's not bother about this equation. This equation says if you try to understand the system loses memory exponentially fast. So this is basically what I'm saying. So if you have a system that loses memory exponentially fast, you have a result. I mean, you have to do the checking. You have a result that you can control the measure of the sets that will give you good statistics in some kind of way. This is called large deviation. What I'm telling you is the following. I noticed that product is going to Birkhoff sum. When n goes to infinity, I want to make n small. What do? I use something that's stronger. It's called exponential decay correlations. If I use this, I can control the measure of the points that will give me good statistical properties for this correlation. So if I do this, I can make n very small. So that's the whole idea. Yeah? If I say that my system loses memory exponentially fast, I can take n small for a very large set of initial conditions. So this is what this result is saying. And the third assumption, this is where weak coupling kicks in. I told you that mu is the invariant measure for the network. And I'm saying that near mu can be a crazy measure. I'm saying that near mu, there is a measure, nu, which is a product measure. So this is an important assumption. And this assumption is not so crazy, although the system is crazy, because if you look at your equations and you say that your equation is stochastically stable, this is always true. Yeah? So this measure mu here, it will couple all variables. I'm saying near this measure, there's a measure that's super nice as a product. Okay, so this is where the weak coupling kicks in, and this is called stochastic stability. So basically I'm saying I'm looking, so if you're more mathematical minded, I'm looking for a system that has decay correlations exponentially fast and is stochastically stable. So under these assumptions, I have the following theorem now to tell you. So the idea is the following. You give me the original system has a S prime sparse representation in a given basis L naught, where my dynamical system is exponentially mixing. So now what I'm going to do, I will map this L0 basis to a new basis, which will be L nu, which is basically the Gram-Schmidt of L0 in the measure nu. Yeah? So basically it's the following, I'm telling you. So I give you the L0, you do Gram-Schmidt of L0, yes? In this and then you get a new basis function that will be kind of crazy, but anyway. So this will be now L nu. So now what I tell you is the following. Let's look at L nu. So the first result is the following. So the map that maps L0 to L nu will map S prime solutions to S solutions, and it can control how much it distorts the sparsity. Yeah. So basically it says like when you map a basis to a new basis, we'll map a sparse solution to a new sparse solution, and is still sparse. And this only works for product measures. So if you put any crazy measures, you lose sparse straight away. Property 2, when the network's very large, then there will be a very large set of initial conditions such that if n, the number of points you measure, is larger than this equation here, then your operator now, from this library, will satisfy the condition we need. Yeah? So there is an equation for n. So basically you determine the minimal n. In this case, a constant uniform only depends on the basis. So this in particular implies that if you try to solve this problem here now, so L nu x equals to x prime, so you try to solve for u. If you do L1 minimization, it has a unique solution, and the solution will be S sparse. So basically, all the ambiguity was gone, so you can precisely reconstruct the system. Any question here? And you can compute everything. So this M is the number of basis functions you have. So it's basically the cardinality of the basis functions. And this S is the sparsity of the solution. Is it clear? So basically it was the following. So I start with a problem that I can never reconstruct unless I measure data like crazy. So if the system is, let's say, chaotic enough, by chaotic enough I mean it has decay correlation, then you can map, you can change the problem. So you give an initial problem L0, you change to L nu. When you change to L nu, you keep sparsity. Then if you measure more data than this, well, I will discuss this equation again, then your operator becomes super nice in such a way that if you try to solve L1 minimization, you only have unique solutions. Yeah? So all the ambiguity was gone, so we are happy. Here. How I check it? Say again?
Yes.
How I check what? No, this is by assumption. So this assumption. Yeah. I mean, I can do formally, so this means like... you say if you give data. I will do with data soon. So if you give data and say check this condition, I don't know how to check this condition. This is usually the mathematics problem. No, I'm saying I have an assumption that if you satisfy this assumption, something will happen. Soon I will do with data. So if I take data, the question is, does your data satisfy this assumption? I mean, this is I don't know how to do it, but I will do it anyway. This you can also try to test, by the way. I will do it soon. I'm saying, so if you give me data, I will do some acrobatics and I will argue that the data is satisfying this, and then I'll do some calculation and do something. I understand your question is the following. You give me data, now I have to mathematically prove that this is satisfied. Then I think this is impossible. But we can always argue that this condition is satisfied for the data. But thank you very much. So to say, the correct statement, if I wanted to do, so instead of doing this, is like, there is alpha naught such that for all alpha less than alpha naught, this theorem reads like this. Okay, so let's go back to this example. You remember, so this is the logistic map, cubic polynomial coupling. So here I had, and the y-axis, false positives, and the x-axis, I had the length of the data. So red curve was the L1 basis per shoot, the classical one. And now the green curve is the ergodic basis per shoot. So, okay, I'm calling ergodic basis per shoots when I use ergodicity, adapt the basis, and do these tricks. You see, after 100 points, bang, solution is always unique. No false positives, no false negatives. Yeah? So what I want to argue now is like this guy here will not scale with n squared as this guy here does. So you really gain a lot of freedom. Is this plot clear? So, okay, so there's this guy. So let's have a look at the equation for this n naught. So basically n naught must be larger than this thing here. So what I told you is that this m is the cardinality of the basis, how many basis functions you have. You can always calculate. I'm using homogeneous polynomials. But basically this will be n to some power. So this will be log n. So I'm saying that everything that's in this log will scale with n, log n. So let me replace this. So I get some new constant because there's some constants here. But basically now this n naught will be this number that appears, that's the sparsity times the log of the system. And this is sparsity here. There's another assumption. So if, for example, let me just discuss this. If f and h are in your basis already, then this s here becomes the degree of your system. So how many connections a given node has. So in this case, the equation for n naught will be some constant that you can compute times the degree of the system squared times log n. So this can be actually, it can be super good. So for example, the degree of the system in this guy here, it was 2. So it does not depend on the system size, basically. I mean, some people believe that log is not a function, right? So basically constant. So this is very good. If this network is random, for random networks, for example, this degree here is p times n. So you get back n squared dependence, but times p. So this can be kind of, still can be a lot less than the original basis per shoot. But if you have, for example, a scale-free network, Barabasi-Albert, if this rings a bell, the degree squared is n. So let's say for a scale-free network, you get back n. So you have to have to get as many data as the size of the network. But usually this is much less. Yeah. So from this decay of correlation, you can see the minimal data points that you get. So this is very, so we like this very much because it says like, even if your system has all the important properties, if you don't measure enough, you will not reconstruct anything good. Yeah. Okay, so this is basically Arkady. This is how we tackle your question. So I'll do a data procedure now. So what did I do here, for example, when I had to do this thing? So what I do the following. I have this matrix here, x1 at time 1, x1 at time 2, x1 at time n, and then I have x big N at time 1, x big N at time n. So I have this matrix, but I would say that they all equally. This is basically distributed. So then actually I'll create a huge vector, x1, x1, time 1, time n, and then x2, time 1, x2, time n, and so on. So now I create this huge vector, and then I estimate the probability measure from this huge vector. And because I'm saying there was product before by assumption, this means like this is a good approximation. So once I get this measure, I can do kernel density estimation, and then I can do the orthogonalization numerically. So this is all what I do. I'll do the experiment as well. But this is the idea of the procedure. Once you get this theorem, so you get robust reconstruction. By robust reconstruction, I mean, if you make some errors in your observation, not in the dynamics, in the observation, and this error is small, then you can prove, okay, if I'm making some error in the observations, then I need to allow for some mistakes in the observation as well, when I do the minimization. And the main theorem is the following. So that now the reconstructed coefficients, given this error, will satisfy this equation when this is the true coefficient. So basically, once you have errors, things will go out of place, but the errors under control in L2 norm. Yeah? Okay. So let's look at this this equation here, and let's do some discussion. Then I'll do an analysis of a given experiment. So first of all, if this L naught is huge, think of some huge number, then 0 will solve this problem. Do you agree? Let's say this is infinite. Then I'm saying I'm looking for the least, the most sparse coefficient that solves this problem here. 0 is a solution. Do you agree? Because basically you can make any mistake. So if epsilon is very large, then 0 solves the solution. Then as you start decreasing 0 and decreasing more and more, you start seeing this problem here. Yeah? You start going back to your original solution. Is this clear? So this is the main observation now. So I'll do analysis of one experiment. So the idea is the following. So I'm going to get noisy data. I'm saying that this noise data is coming from an ergodic dynamical system. I will estimate the probability measures for this ergodic dynamical system. Then I'll do the basis adaptation, create this ergodic basis preshoot. But this is noisy. So what do? I go back, and I know that if I increase epsilon too much, then I see 0. Then I keep on decreasing epsilon. Then I see isolated dynamics. Then I keep on increasing epsilon. I see some connections popping in. I keep on decreasing epsilon. I see still connections popping in. Then I keep on decreasing epsilon. Then I will see false connections, just by the statement previously. So what I'm saying is the following. There is, by construction of this theorem, there must be a range of epsilons that if I solve this as a parametric family of problems, there will be a range of epsilon where the connections will be robust. So no false positives, no false negatives. Yeah, this is the theorem. So because this workshop was called Applications to Neuroscience and Beyond, I went for the Beyond. So I have application neuroscience, but I will do application for the experiments that some friends of ours did. This is lasers, couple lasers. So okay, so in their network they have 17 lasers. They are diffusively coupled on network. So if you have a look at the data is basically this. So here's the Y is the measurement, the electric field for each laser they measure. So I'm plotting here for all the 17s. So I'm plotting Y or time t, Y at time t plus 1. This is called the return map. And you see that the system is all over the place. But when you look at the histogram, let's say the visitation time that they spend in a given area, so basically around this part here, there is no measure. So what I will do, I'll chop the data here. I will only consider the data where the actually measure is significant. Yeah, and already here you see that basically there are two groups of nodes, right? One group of nodes following this measure, one group of nodes following this measure. So by assumption, I will say there's a product measure of two groups that are packed together. So what I will do then is you don't seem to like this figure. Yeah? So, okay. They gave me a lot of data. I'm telling you that a lot of data was not good. Why? Because basically the system barely hits here. If I include this data in the problem, I only get false solutions. So I will throw some junk of data away. I will only get data that visit here. So look for time windows of that they jointly visit this area, and this are distributed according to these guys. There are two groups of nodes, so I'll say that my measure is a product of two given measures. Is this clear? Okay. So I discard some regions of small density, and I look for a product measure that approximates the data. So now when I do this, I get this parabolic shape. And this is the product measure I was talking about. So I do some clustering. So I learned that from nodes 1 to 5, I have a given measure that describes them. And from nodes 6 to 17, I have another measure. So I'm saying I estimate this measure by this kernel density function. And then I say that the true system is described as a product of these two measures. So then I do this path relaxing, what we call. So it's basically I start for large epsilon, keep on decreasing. Or you can think that you start with small epsilon, keep on increasing. There must be, by construction of this theorem, there must be an area of epsilon where you have neither false positives nor false negatives. So this is the original network. So let's go through this picture here. This is the original network. I will focus on this node here. This node is now here. This is the true connections of the node for this parameter, and this is the false connections that if I solve the problem I get. So now I increase the threshold and resolve the problem. You see, now I have less false connections. Then again, I increase the threshold and resolve the problem. So basically now, no false connections whatsoever. And here now, I'm plotting the number of false negatives in pink and number of false positives in orange. So this is what you see. So there is an area here where you have no false positives, no false negatives. If you keep on increasing, then they will jump up again by construction, right? So this is what is set. So 0 will be a solution, so they must be negative. So around this value here, you have a very good network reconstruction. What this is important is the following. I did not need to know any particularities of the noise if I can do this parametric family, right? But this is costly. But if you're able to solve this problem as a parametric family, you do not need to know properties of the noise. Yeah. So I'm about to finish. Let's just recap what we did. If you use optimization techniques and ergodic theory, then you can guarantee uniqueness of solutions, and the solutions are stable. So this means, like, if you're really interested in solving a network problem, you really need to know dynamical systems, basically. I mean, you need to do something with dynamical systems. So basically, if you use that they preserve probability measures and so on and so forth, you can adapt to original problem, and your solutions will be stable now. And this will depend a lot on how much you measure and so on. Then there's another problematic point here is that you need to estimate these measures from data. So this is usually very complicated. Here, because you're saying there's a product measure that is strict. In general, I agree with Arkady. This is a super complicated problem. So for example, this is a bottleneck. So if this measure is not a product, then basically you don't have enough points to sample the measure, so you can never find the measure. And this is something here maybe we should discuss later. So large deviation will appear in this calculation quite heavily, and how to do large deviation for networks and so on. So I think this is an opportunity for these people that are super clever in large deviations. I think there's quite a bit of opportunities. And how to prove that your network will will satisfy large deviation for what kind of observables, whether your basis that you had originally will satisfy large deviation, what's the large deviation exponent, and so on. So improving this will all improve the length of measurements that you need to do. And so as we're discussing here, this is for weak coupling. If the coupling is very large and the system synchronizes, this is a trivial problem again. But if the coupling is such that this is not weak, that this means like there's no product measure that will approximate the measure, then we get total darkness again. So I don't know what to do. Maybe, I don't know. So I think we need new ideas then. Okay, thank you very much for listening.